there's links in them. So a lot of things will just have like hyperlinks. So you'll be able to see that. But my name is Drew. I live in Berlin. So I'm an hour behind y'all, I think. I'm from Chicago, though, in the US. I moved to Berlin last year. And then I met Ron because we were both speakers at Virtual FOSS North last week, I think it was. And then he told me about your group. Here in Berlin, we run an embedded Linux meetup. So hopefully this will be a good lesson for us, and we can try and have a virtual meeting as well. I'm not sure if anyone was able to join, but I also shared this link with the people from my group here in Berlin. So just a little bit about me. I work for a company that makes circuit boards, so I design open source hardware projects for that. I'm also part of the BeagleBoard.org Foundation, so we make small open source Linux computers like the BeagleBone, and I'm also part of the Open Source Hardware Association. And since this talk is about Linux on RISC-V with open source hardware, I wanted to just very quickly talk about what open source hardware is. So it's hardware whose design, so we're talking about the design files are made publicly available so anyone can study, modify, distribute, make and sell those designs, or hardware based on the design. So essentially taking the ideals of open source software and putting it into the context of hardware. So I mostly do electronics. So if we talk about this in the context of electronics, you'd be sharing the schematic in the board layout, and it would be the CAD files from the software using like KiCad or Eagle or Altium, and then also the bill of materials. And then the best practice would be if you're designing some hardware that you want to be open source, to make the parts available, make sure you're using parts that are available in distribution. So just kind of a quick overview there. And I would say sum this up as saying open source hardware makes sense when you want to enable collaborative development on your project. So if that kind of fits with what you're trying to do, it might be a good fit for you. And we're going to look at some boards today or tonight that are open hardware. I go more into this in this talk I gave recently at this hacker conference in Germany. So you can click on that link in the slides if you want. But let's talk about RISC-V. So when you write a program like a C or C++ program, it gets compiled into instructions for the microprocessor to execute. But how does the compiler know what instructions the CPU understands? So this is defined by the instruction set architecture. So this is a standard. It's a set of rules that define what tasks the processor can perform. So examples you've probably heard of. Were you saying something, Ron, in the chat? I don't know. I saw something pop up. Oh, never mind. Anyways, so you probably have heard of x86, which is the Intel/AMD instruction set. So this is very common on servers and laptops and workstations. And then if anyone has a smartphone, which probably most of you do, it most certainly probably has a ARM instruction set in it. However, both of these instruction sets are proprietary, and you have to license them if you want to use them. So RISC-V came about 10 years ago. There was researchers at the University of California, Berkeley, and they were doing computer architecture research and didn't want to bother with licensing a commercial instruction set like ARM. So they decided to come up with RISC-V. It's 5 because it's the 5th RISC architecture to come out of Berkeley. Berkeley was one of the places back in the early 80s where the whole idea of RISC came about. So this is a free and open standard. It's a Creative Commons license. So anyone that wants to can take this standard and implement it. I'm not going to go a whole lot into the instruction set today or tonight, but these are 2 great talks. One is by David Patterson. It's called Instruction Sets Want to Be Free. And he's actually the co-creator of the original idea of RISC back in the early 80s. And then Kirst Asanovich is the one of the professors at UC Berkeley that started this project as well. And every year, maybe once or twice a year, he gives a State of the Union of RISC-V. So it's changing pretty rapidly. So if you type into YouTube like RISC-V State of the Union, you'll probably find the most recent one. So this is the State of the Union talk, and then I just borrowed from there a couple of slides. So the idea of RISC-V is that it's simple compared to other things like x86, which are massive instruction sets. It's also designed around the idea of being modular and extensible. So RISC-V is something that was designed to be able to scale from small microcontrollers all the way up to supercomputers. So the idea here is also for it to be stable. So the base instruction set is frozen. So even in the future, if you have some crazy 128-bit RISC-V computer with all these new extensions, it'll still run a program that was compiled for the base instruction set. So I was talking about it's been around for about 10 years. And then in the last several years, companies have gotten involved like Western Digital and NVIDIA. The other important thing is it's not the first open instruction set. There's things like OpenRISC and other open instruction sets, but RISC-V is one that's really gotten traction. And it has kind of critical mass. It has support in Linux, GCC, LLVM, several different real-time operating systems. There's also open source implementations from like Boom and Rocket from UC Berkeley, and at ETH Zurich, they have the Pulp team there, which does some other cores, and there's teams in India that are doing them as well, and even like Western Digital has contributed Swerve, which is an open core. So there's a big ecosystem that's continuing to grow here. Now the base ISL, the base instruction set itself is just 32-bit integer. So it's very simple base instruction set. So that's all the instructions right there for RV32I. So you'll see a lot when you look at RISC-V, these letters and numbers. So RISC-V 32-bit, there's also RV64, and yeah, so there's 64, and then even 128, which is this kind of a theoretical thing now, but in the future it might be something that is useful, particularly for security. And then these other letters are multiply, accumulate, float, double float, and then compressed. The A is for atomic. So these are extensions to the base instruction set that may or may not be implemented in a design. And then that green card there is actually all of the instructions from the current extensions. So you can see it's actually pretty small, even with all the different extensions, as compared to like x86, which is a really giant instruction set. Yeah, so it was created by the team at Berkeley, but now there's the RISC-V Foundation, which is a nonprofit that maintains the standard and has working groups that are working on extensions. And companies like NVIDIA and Western Digital are planning to ship millions of devices. So Western Digital is switching out the cores in all their disk drives to be RISC-V based. NVIDIA is also putting these controller chips into their GPUs for management that are RISC-V. So this allows them to avoid ARM licensing fees, which if you're making like 1 billion devices can add up, but also it gives them the freedom to do, to leverage open source implementations and also have freedom when it comes to the microarchitecture. So only a few companies actually are architecture licensees of ARM, like Qualcomm and Apple. Everyone else is just licensing specific cores from ARM. So they don't necessarily have the liberty to modify the microarchitecture to best suit their needs. And I should note here too is that RISC-V is an open instruction set specification, but you can both have closed source proprietary implementations of RISC-V and open implementations. So if someone says RISC-V, it doesn't automatically mean that the processor implementation is open source. It just means that it's implementing an open instruction set. And one of the places I've learned a lot is by watching the videos from the RISC-V workshop and the RISC-V summit. So if you check out RISC-V on YouTube, there's lots and lots and lots of talks there. So it's a good way to stay informed. One of the other things that is quite interesting, I think, is there's a big focus from several different countries on RISC-V now. Like India has made it their official, India and I think Pakistan have both made it their official instruction set. And companies in China are fairly heavily investing in it now, especially with things like the US saying no businesses can work with Huawei and these other restrictions like that. Both companies and countries are wanting to have more control over technology, and RISC-V can make them not rely on Intel or AMD or ARM. I wrote a column in Hackspace magazine that you can download for free if you want to have some more information on this. However, the first time I ever heard of RISC-V was there was this organization called OnChip at a university in Columbia, and they created a completely open source 32-bit microcontroller called the OpenV. Now this only has a couple kilobytes of memory, so it's not something we can run a full operating system on. But it was pretty cool because it's the first time I'd seen someone make a chip where the implementation of the chip was all open source, which I thought that was pretty neat. Another organization that I'm quite excited about is Low Risk. So this was created by a few people that helped start Raspberry Pi, Alex Bradbury and I think Rob Mullins. And the idea here was they wanted to create a not-for-profit organization in the UK with the hopes of producing a system on chip, or SoC, that you could use for making something like a phone or a single-board computer. They're still working on that, but they do have ways for you to try out their kind of in-development version here if you have this FPGA development board. So if you're interested in that, you can check that out on that link there. Another organization that's important in the RISC-V open source chip design world is FOSSI. So this is a not-for-profit that focuses on free and open source silicon design. And specifically, they operate a couple of different conferences throughout the year, OrConf in Europe, LatchUp in North America. They were just about to have an event in Istanbul, but that was canceled. So we'll see when conferences come back. But if you check out on YouTube, there's recordings from all these conferences. So if you want to find out more about any of these topics, there's many talks on YouTube that you can look at. LibreCores is an initiative out of FOSSI that is kind of trying to be a place where people can go to find proven implementations of digital logic, things like cores and controllers and things like this. So, I need an Ethernet controller. The idea is you would go to LibreCores and find an implementation that you could put into your system on chip, or SoC. So Sci5 is a startup that was created by some of the people at Berkeley that created RISC-V. And they came out with this microcontroller called the FE310. It was one of the first commercially available RISC-V microcontrollers, and here it is in the Arduino-style form factor. So it's an interesting chip, but I'm more interested in Linux, and this one, unfortunately, only has like kilobytes of memory, so it's not quite a good fit for Linux. However, a little while later, they came out with a chip called the U540. So this has four 1.5 gigahertz, 64-bit RISC-V cores. So a very capable system. So this dev board here, the Hi5 Unleashed, is probably the best board that you can get if you wanted to run Linux on RISC-V. However, it was primarily made as a valuation sort of board, and they made like less than 1,000 of them. And the board itself, because they made so few, is I think $1,000. So very few of them are available, but some of the places you'll find them are with people that are working on distribution. So people at Red Hat have been bringing up a Fedora port of RISC-V. So here's an example of it running on that Hi5 board with some additional hardware. It's a very expensive solution here, costs several $1,000s, but this is important for people that are doing work on distros right now, like Fedora. So this is actually a full graphical Linux desktop running on a RISC-V chip right there. Now, one of the other tools that people that are working on things like bringing up distros are doing is they're also using QEMU. So here's the really expensive real hardware with this i5 Unleashed board, but then also you can use things like QEMU to do a lot of this bring up and development with an emulator on a powerful x86 system. Here's just an example from the Red Hat team that's working on Fedora of whether we're in QEMU or we're with the actual Sci5 board, kind of a similar flow there of OpenSPI is kind of like brings up and initializes the hardware, and then that jumps into U-boot. And U-boot's very standard for embedded environments. So and then we boot into Linux, and then we boot into the full distro. So kind of a flow that we're used to with this OpenSPI in front of it. Now, Debian is also doing a port of RISC-V as well. So right now there's both Fedora and Debian if you have one of these systems. You can also, with both Fedora and Debian, just download it and run it on with QEMU on your system, or another emulator that I'll talk about at the end. So if you want to, you can just run this right now on your laptop or on a server. However, that's not so much fun, and I think this is an embedded meetup. So what about like actual hardware that we can get our hands on, since that Sci-Fi board is expensive and hard to get? So this little board here has a chip on it called the Kendrite K210. And this can actually run Linux. So the board I showed up there is only $13. It's from a company called Cyped. It's called Max Bit. And it has the Kendrite K210, which is a dual-core 64-bit RISC-V processor running at 400 megahertz. It has 8 megabytes of SRAM, which is a lot of SRAM for a microcontroller, but it's relatively small when it comes to Linux. So Damien the Mall and a couple of Linux kernel hackers for the last like 6 months or more, I've been hacking on trying to get Linux to run on it. And they finally did. And now there's really clear instructions that you can go through and get Linux running on it. So down at the bottom here is a link from CNX Software where they go through the whole process of how to get Linux up and running on this chip. Here's another picture of the Cyped Max Bit board. It's running Linux 5.6, which is mainline. And you can see there it has dual core RISC-V RV64 cores, and then it even has a little C compiler on it, so you can write and compile C programs. It only has 8 megabytes of memory, so it's a little bit trivial, but also it's the best way we have right now for a little bit amount of money to actually see Linux on RISC-V. This is another board with that same microcontroller. This one also has a Wi-Fi chip connected over serial, so someone's actually working on trying to get networking working. So if you're interested in like low-level things like the Linux kernel and build root and kind of low-level library stuff, if you get one of these boards, it's a great chance to get involved right now. There's a lot of work that needs to be done to get it working better. And you can even, if you don't want to compile everything, you can also just download this image and throw it onto the board, and it'll be running Linux. So the Kendrite chip's pretty fun, but you know, it's limited in its utility. So if we want to have something in the future like a BeagleBone or a Raspberry Pi that's RISC-V, we're going to need an actual like system on chip or SoC that has external memory. So like DDR interface, that sort of thing. So Microchip has a chip coming out called the PolarFire SoC. So this is actually similar to the Xilinx Zinc, where it has a hard ARM core along with the FPGA. So this one has a hard RISC-V core along with an FPGA. So because it has an FPGA in it, it's going to be kind of expensive. So the other thing that's happening this year that I'm excited about is the OpenHW group is a nonprofit firm from several different silicon companies, and they're going to produce this test chip called the Core 5 SoC, and this is basically going to be the NXP IMX style system on chip. Like you maybe have seen the IMX 6 or IMX 8. They're really popular for embedded Linux systems, and they're basically taking the ARM out and then tossing in a RISC-V core. Oh, here's a picture actually. So you can see here, has similar peripherals that you'd see like maybe an IMX6, but instead of that, you have instead of an ARM, you have the 64-bit RISC-V core in there. So I think this is really exciting. They're hoping to tape out, which means fabricate the test chip second half of this year. So maybe next year we'll see dev boards with this chip. And I think a chip like this or something similar is what we're going to need before we can start making, you know, like a sub-$100, you know, Raspberry Pi, BeagleBone style board. I'm interested in trying to get a board like that made. We don't have a chip yet really that we can do that with, but if you're interested, get in touch. It'd be cool to have like an open hardware board with one of these sorts of chips when it comes out. However, the one thing we do have available for us right now is FPGAs. And I can't go all the way into what FPGAs are right now. So if you want to learn more, Megan Wax of Sci-Fi gave a great talk at the Hackaday Super Conference last year. You can check that out, that link. But if you've not heard the term before, FPGA stands for Field Programmable Gate Array. And you can think of it as a chip where it doesn't have a fixed function. It just has a big sea or ocean of logic gates that we can configure to whatever sort of digital logic we want it to be, including a processor core. And I learned FPGAs a long time ago in school, and we had to have these giant proprietary software programs or IDEs on Windows to be able to run them. And even though that they now run on Linux, they're still giant. Like I had to install the one from Xilinx, and it was like 50 gigabytes, or something crazy like that. So a few years ago, Claire Wolf made a big step forward with FPGAs, where there was created a tool chain that's all open source. So for this FPGA from a company called Lattice, the ICE40, you can use entirely open source tools to go all the way from the Verilog, which is the hardware description language, which actually is describing the hardware logic that you want to be on the FPGA, all the way to the bitstream, which is essentially like the binary that gets loaded into the FPGA, all of that using open source tools. And then another person, David Shaw, started working on a more capable part called the Lattice ECP5. And we were excited. One of the reasons to be excited about the ECP5 is actually big enough to be able to put a RISC-V core into it that can run Linux. And then more recently, so Xilinx, I mentioned before the Xilinx Sync. So Xilinx is definitely like the market leader when it comes to FPGAs, and they make the bigger FPGAs, the one that are much more capable of functionality. The sorts of things you find in cell phone base stations and like cinema cameras and these sorts of things. And there is a group, Project X-Ray and SymbolFlow, that are trying to get open source tools working for the Xilinx Series 7. So I think once that's, and that should be in the next couple of months, Tim was telling me, then it's really cool that you'll be able to use open source tools on these bigger FPGAs. I wrote a column in Hackspace, talks more about the open source tool chains. You can check that out. And then one of the things I wanted to talk about here is kind of the last section here is about a project that me and some other people worked on. So it looks like there was a question about the Zinc. So the Zinc is a FPGA where, in addition to the FPGA fabric, it has a hard ARM core. So it means we don't have to waste the FPGA logic gates to implement a processor. We can use that for our special functionality. So the Zinc has a hard ARM core, which is great. The idea with that microchip PolarFire is that it has a hard RISC-V core alongside the FPGA fabric, which I think will be quite exciting, but I think it's going to be kind of expensive. The pricing isn't out on it yet. Oh, there is no connection specifically to Zinc. So another thing to note is that I don't think the PolarFire is an open implementation. It's, I think, leveraging some open source cores. But the other thing to note is in the chip design world, most of the open source projects are all permissively licensed or non-reciprocally licensed. So you oftentimes will see commercial chips that might be using one of these open cores from a university, but the implementations themselves are like the actual product itself might not actually be an open implementation. So the project I wanted to talk about was we went to this conference last year called the Hackaday Super Conference, and a lot of conferences these days have cool little like hardware badges. So this one was in the shape of a Game Boy, and it had the ECP5, the Lattice ECP5 FPGA on it, which is a big enough FPGA to actually fit a lot of neat things into, like a soft core. So the idea here with this badge was it would like have video games on it. You could program it to have different graphics, like display your name, that sort of thing. But me and some other people thought it'd be fun to try and get Linux running on it. So Michael Welling, Tim Ansel, Sean Cross, Jacob got together, and through the 2 days of the conference, eventually got Linux running on it. It had 16 megabytes of SRAM built into it, but we ran into issues with that. However, it turned out Jacob, before the conference, saw the design of the badge and made this add-in board that went into the back that gave it 32 megabytes of SDRAM. And that proved to be enough memory for us to be able to run Linux. This is the back of the badge where it has the expansion connector that this board goes into. Now, I was talking about soft core. So what does it look like when you take that big ocean of logic gates and configure it, wire it up to be a Linux-capable RISC-V core? So this is someone on Twitter that had a cool visualization at kind of a macro level of what that looks like, just to give you a sense of what it looks like to have a soft core loaded into an FPGA. And then what we actually used to do this was Python, which is kind of surprising. So typically with FPGAs, you're using hardware description languages or HDLs like Verilog or VHDL. But there's actually a way to do this with Python. And it's using this framework called MeeGen, which is a Python-based framework that allows us to describe the logic of our chip in Python, and then it produces Verilog, which is the traditional hardware description language that you use with FPGAs. And just to give you a little flavor of what it looks like, here's an example of blinking an LED in the MeeGen Python framework. So I don't know how well you can see this, but on the left-hand side, that's Verilog, which is traditionally, or sorry, that's VHDL. So most things are done in VHDL or Verilog. So that's an example of a flip-flop, which is a basic digital building block in VHDL. And then here's the example of doing it in Python with MeeGen. So that's just describing the digital logic. But if you want to make a whole system on chip, you would have to implement all these different things. However, LiteX is a project based on MeeGen and another project called NESOC that allows us to pull together all the different parts of a system on chip to build something specific to our use case. So LiteX is basically a collection of cores and controllers that we need for building a full working system. And this is all written in Python. So I think here's a better picture of it. So you can see here we have LiteX, which pulls in MeeGen, which is that Python framework for doing chip design in Python. And then we have the open source FPGA toolchains. And then LiteX has this ecosystem of different cores. So things like DRAM controller, Ethernet controller. This Hackaday badge only had serial and DRAM, but much more expensive FPGA boards might have older features like PCI Express or SATA or Ethernet. So this gives you implementations for those controllers. And then for the badge, we leveraged this project called Linux on LiteX Vex RISC-V. So Vex RISC-V is a 32-bit RISC-V core. It's an open source implementation that you can pull into this project and use on FPGA. And then this project itself on GitHub, you can go to it and it gives you everything you need to basically boot up Linux on FPGA. So in our case, we were using the Lite DRAM controller. So we didn't have to write our own DRAM controller. We could just grab the one from LiteX. Same thing for the serial controller. And this is what it looks like for Linux on LiteX Vex RISC to boot up on an FPGA. And then here's the badge running Linux. The screen here is not working yet. So it's actually connected to a terminal emulator on my computer here. And then it's just running a very minimal Linux userland. It basically has a BusyBox that was built using Buildroot. And then once we got back from the conference, we got all the changes we made upstream back into the LiteX project, which may not be that useful because you don't have the Hackaday badge probably unless you're at the conference. But if you want to take a look at what does it look like to add a new board to LiteX, I think this is a good example of what you do. And the cool thing here is, it's in Python, so we're leveraging the object-oriented nature of Python. So we don't have to write everything from scratch. We can basically just take what's already there and just add in the specifics for our board, or the Hackaday badge in this case. So this is a file where we are specifying the pins on the FPGA and what hardware connectors they're wired up to. And that's in Python there. And then just to give you another kind of flavor for what MeeGen looks like, we're importing different libraries from MeeGen to give us things, MeeGen and LiteX to give us things like the clocks framework and DRAM controller and these sorts of things. So rather than having to write everything from scratch in one giant file, we can pull in the different modules as we need them. And this is what it looks like for us to add our board essentially to the build system. And with our board, we're using this base system on chip class, and then we're just adding serial because we don't have anything else on our board. But other boards might have like HDMI or PCI Express or these other things. Ours is a pretty simple board here. And the other thing I wanted to show was we're using an SDRAM chip on the badge in that expansion board. And that SDRAM chip was already in LiteX. So we actually were able to add that to the Lite DRAM. module, and we didn't have to like rewrite the whole thing from scratch. We were able to just take this SDRAM module class and just extend it for our chip. So all we had to do is go to the data sheet for the chip and grab the specific numbers, like the timings and stuff like that, put that in there. So I think this is a kind of a nice example of how with Python you can leverage the object-oriented nature to keep you from having to write a bunch of stuff from scratch. Myself, I'm not experienced with Verilog or VHDL, so for me it was much easier to understand what was going on here because it was in Python. And let me take a look at questions here real quick. So the Python, the MeeGen is using Python, and it's just using Python to produce the Verilog. So Python's not running itself on the FPGA; it's running on your computer. That's then producing the Verilog that goes into the synthesis and the place and route. I don't know how multi-threaded it is, but in my experience, like running the MeeGen in LiteX builds, it's pretty quick. So I can build this whole Linux on LiteX RISC system in a few minutes. So it's not too. I don't know if it's multi-threaded or not, but it runs pretty fast. And MeeGen creates the Verilog files. I'm not sure what UCF is, but it pretty much takes care of everything you need for getting it into the FPGA flow, so you can have the synthesis and the place and route and get the bit stream out of it. Okay, yeah. So
you're on mute.
Oh, how long have I been on mute?
Not long.
Okay.
I think you just from when after you answered the question.
Okay. All right. So someone was asking about UCF files, which I guess is normally how you specify the pins. So in this MeeGen framework, in these LiteX modules, you do the pin constraints in this sort of setups here. So you have like a file where you define the pins. This is where we're defining the pins, and then essentially what we're going to get out of LiteX is a bit stream. So we don't have a separate file that defines the pins outside of Python. And let me scroll down here. So yeah, I was talking about how it was cool for us to add in the memory chip and by just extending this class and putting in the information from the data sheet. So we got done with all this, and it was running really slow. It was taking 300 seconds to boot, which is not very fun. So I thought this was a neat example of open source project working well. So I opened up a GitHub issue, and his name is Florent. His username's Enjoy Digital. He, within like an hour, saw my issue and figured out how to make it go faster and sent in a new commit. I pulled it in, and now it's booting 10 times faster. So I thought that was a fun little moment. And if you've not seen it before, ASCII Cinema is quite nice. It allows you to record your terminal and play things back. And that made it really easy for me to show Enjoy Digital what was happening and also share with other people what it looked like when it booted up. Yeah, I was talking about the optimization here. And by the way, this is what it looks like when you launch it from the terminal. This JSON file actually specifies where the kernel is, where the rootfs is, where the device tree is, and then what memory addresses you want to load it into. And then it transfers it over serial into memory and then jumps in and start executing. And then to give you a little idea of what the optimization was, this is not all of it, but one of the things that Enjoy Digital optimized was for this badge, we only had 8-bit wide SDRAM, which is not great. So it was having to access memory a lot and relatively slowly. So he made the L2 cache wider, which allowed us to not have to go to memory as often. So that was one of the things that optimized it and made it boot much faster. And I thought this was neat because if this was Verilog or VHDL, I think it would have been more difficult for me to look at this and kind of get an idea what's happening. But because it's in Python, it's easier for me to look at, and probably most other software engineers. And then you might wonder, what about the screen? So Greg's an awesome hardware hacker in Australia who was also at the conference. And like maybe 3 or 4 weeks ago, he finally got the screen working using Light Video, which has a VGA terminal emulator. So it's you can see Linux boot up on there, and someone was joking we should add in a keyboard connector so we can plug in and actually type on it. So maybe we'll do that. So if you weren't at the conference, you wouldn't have one of these badges, but there's other open hardware boards that have the ECP5 FPGA that are capable of running Linux. David Shaw, who did work on the tool chain, that did a kind of mega board with everything you could possibly want, but it's very expensive and it's not sold. It's just open source design, so probably not super practical. But there is this board from a hackerspace in Croatia called the Radiona ULX3S. It's currently funding and crowd supply. It has ECP5 FPGA and 32 megabytes of STRAM, so pretty similar to what we had on that badge there. And then another one that I'm very excited about, Greg produced this. It's called the Orange Crab, and it's in the Adafruit Feather form factor, which is quite a small form factor. And there's lots of wing boards, which are the expansion boards that can fit onto it. And this one has 128 megabytes of DDR RAM, so a good amount of RAM that's much faster than the SD RAM. And this can run the LiteX on Linux Vex RISC-V quite well. And it's currently funding on, yeah, there's an example of Linux booting up nice and fast on the RISC-V core in that FPGA with the Orange Crab. And the Orange Crab is also right now available through crowdfunding on GroupGets. And it ends on the 13th, so you have like a week left if you want to look at that. Though it may not, if you're new to FPGAs, it might not be best to start with one of these bigger boards and try and run Linux. Sometimes a smaller system's better to learn. So there's this board called the FOMU that has the smaller ICE40 FPGA, and it has a really nice self-paced workshop that you can do there on this website. And it shows you how to blink an LED first in MicroPython, then in Verilog, and then in LiteX. So it takes you through these different contexts, which is a nice way of learning. And this, you don't have any hardware. I mentioned QEMU, which is one way to do it, but there's also this emulator called Renode from Antmicro. And this is a really nice way of doing it because it has the several boards already set up in it. So take a look at that page here. There's things like the Sci5 board, and then also the Sci5 Unleashed, which is that really expensive board that's hard to get. And even the FOMU. So all these ones you can run in an emulator where it's all set up with the peripherals and everything. So it feels like you actually have the board connected to your system. And then here's an example of me booting up that Hi5 Unleashed board in Renode on my laptop. So you know, it's that board that's $1,000. So you don't need that board to be able to experiment with the software environment. You can just run it in Renode there. And here's the link to the slides if you didn't see it already. And hopefully that wasn't too long. Are there any more questions that I didn't answer? Someone's asking about zinc. I don't know if I answered that fully, but hopefully you all can still hear me. So if people type into the chat, I think I can see that. Or oh, thank you, Ron. Yeah, I think the really cool thing here is that MeGen, which is this essentially domain-specific language in Python, lets you do chip design in Python. And the people who find the hook behind the FOMU, I think they're very excited about getting software engineers into chip design with things like MeGen. And I didn't mention it. Let me just pull it up real quick here. If you just have your computer and don't have any hardware and you want to learn MeGen, you go to Lambda Concept. They have a blog here, and they have a nice tutorial here that takes you through MeGen step by step. And I think if I look here at the Hello World, here's an example of blinking LED. If you don't have hardware, though, you can use this program called GTK Wave, and you can actually see the LED line go high and low. So you can actually write this MeGen code and actually do the simulation all on your computer. Don't need any hardware to start. I'll paste it into the chat here. So I think we have other speakers too, I think, Ron, if that's correct. Hopefully. I want to learn some stuff too.
All right.
Oh, should I stop presenting? Oh, maybe that would help.
No, it's okay. It's okay. But so thank you. Any more questions, guys? I mean, I think it was technically okay. No, like no special technical problems, right?
Yeah, I think it worked pretty good. Yeah.
Yeah. I mean, and people are very disciplined, especially Mr. Toxic that muted the one single non-disciplined person. No, so thanks, man. Okay, so I actually think like I think it's okay like to jump in with questions, also not in chat because it's going to be a little bit difficult to get it right. So all right, so thank you so much, Drew, for presenting, and
Yep,
let's go and present the next presenter, which is myself. Okay. But before that, let me share the screen, and we're going to do a little ruffle, okay? All right, so let's do this. Dun, dun, dun. It presented the wrong tab. Okay. So let's do this. I missed the chat here. Let's see. Okay. So apparently you can't see the chat window and do the present. No. Okay, okay. Now it's supposed to be on. So can you see my screen?
Now, yes.
Good, good. All right. So thank you, everybody who bear with us, despite the technical problems in the beginning. Apparently, there are 3 different modes in Google Meet. One is what we're having right now. The second one is a stream that apparently is not available for everyone. And the third one is something called view-only stream that apparently is not visible to everyone. And I couldn't update the meetup.com event once it had started. So it's totally on me. My apologies. If you were patient enough, then I thank you. So thanks, Drew. The next 2 lectures are going to be, the first one is going to be myself. I'm going to talk about building minimal Linux distros. Some of you who might have been in one variation of this talk, and actually encourage you to go ahead and do things with me if you already did it. Like I always have some extra things, and what I'm going to actually do is like in my GitHub, there is going to be this guy, Renew a PSCG Mini Linux Workshop. And over there, there are several branches that actually in the next couple of meetups, or maybe like in the next couple of weeks, I'm going to show some concept like time after time, okay? So what is going to happen now, as I mentioned I think like in the meetup.com email or one of these things, is that I'm going to do a little ruffle. If we're going to be more like 100, there are going to be 2, maybe there will be 2 anyway, for some free courses or certifications from the Linux Foundation that were nice enough to contribute such. For those who asked me, no, it's not for the instructor-led courses. So unfortunately, no Linux kernel internals or debugging or Yocto project on that. And it's also not like for my courses for the Android internals and so on. What it is for is this guy. Like if I go to the pscg.com, then I have this tab of training the Linux Foundation. And over here, you have an instructor-led training that is not being offered right now, but I'm going to give you good prices if I teach, and good prices if anybody in the Linux Foundation teaches. Like you'll get a discount, at least 15%, probably more. And I mean, these guys, like online self-paced training, the one who don't say free, then they cost $300. So we're going to ruffle now. one. And same for the Linux Foundation certification that I didn't write. I just put like the logos. There are all kind of this. I'm not going to talk too much of it. If you want like a nicer looking website, go to linuxfoundation.org, right? But I'm going to ruffle those. And of course, like if you want, like as I mentioned, like in the Facebook or the Meetup, or I don't remember where, if you want discounts for these things, just talk to me and I'll take care of you, okay? I'm training partner of the Linux Foundation, and I can do that. And for the other courses, are not the only courses. There are all kinds of courses over Android internal tabs and over cybersecurity, and of course the things that I don't publish, because we do a lot of things like with the government and stuff like that. And because I work with my clients more or less, right? So regardless of that, what we're going to focus on is free content. And I hope, and I'm super happy to receive requests, as long as I know that there is like an audience, that we can go and do several sessions and build together some kernel stuff, some embedded distros with tools that everybody may have at home. So I'm going to mostly focus at QEMU that Drew mentioned earlier. And like you will not need like, like TTL, TSB, serial cables, FTDI to go and buy all kind of things like that, or like a particular hardware, especially at this time. It's always nicer to do with hardware, but it's not always possible. So the raffle is going to be like this. For those who registered over this form, then there are numbers, okay? I'm not going to reveal too much here, but there is like a spreadsheet and numbers, and I'm just going to select a random one. So let me just quickly have a look. What is the number here? Yeah, so 44. So we have this super crazy script that is called random byte that doesn't do much, and the winner is line 27. So I will see who it is. I'll send him an email, or her an email, or them an email, and they can select one of the certification of the Linux Foundation, or one of the safe self-paced courses, and I'll give them like a code, and they'll get them for free, okay? So congratulations, number 27. Woohoo, all right. Now, so having said that, let me go ahead and start with my talk, unless you want to take a quick break. What do you say? Break, or we're on? You can jump on the microphone. You can continue.
I say break.
Break?
I'm for going on.
Okay, so I'm just going to shut up for 15 seconds, and this will be a very short break, somewhere in the middle, okay? All right. Okay, so we're going to have a break after my session, okay? And I will try not to make it too long, and I will try not to make it too thorough. Please interrupt me whenever you want, okay? Feel free, like jump over the microphone. If I don't like see, you can ask also over the chat, but I'm likely to miss it, all right? So here we go. Okay, so, all right. So that's going to be me, and I'm going to switch between this and like a terminal. So here goes. So I suppose at least half of you know me from our meetups in Israel, from other conferences, from I don't know where. And my name is Ron Munitz. I lead a company that's called the PSCG. It's part of PSCG Holdings that do all kinds of other things. All of them are technical in this way or another. And I organized this meetup, which is called EmbeddedIsrael, but now it's embedded everywhere and takes place on Earth, just like for North before us. So this is like pretty much like a copy of that slide. And there is a link for that on my Twitter, I think, but I will post it anyway because I also like updated some of the things. And this is like a skeleton. It's going to be used in order for me to actually walk you through all kinds of things. And I do it a lot. Sometimes I pick all kind of other topics, but when we do the next series of lectures, if there is interest, then we'll mostly work with terminals and perhaps with some of the GitHub code that I have, all right? So like, it's not like a commitment, and all right, so that's it. So this is like me. I'm also a training partner of the Linux Foundation, also do work for ARM. I have been involved with several startups. Some are pretty much stealth mode. One of them is doing pretty well. I left the less famous one in 2014, where we developed display protocol for Android. Things, and I'm actually very, very, very active in Android internals these days, both in like the security perspective and in the building perspective. So stay tuned. We do all kind of training. We do all kind of consulting. I now actually do a lot of consulting for fun, and I am actually given this talk, and because I know that like in a talk you cannot get into all the things that you want to do, and I actually started uploading some of the videos of what I intend to, how I build things, okay? So they're going to be in YouTube, and there is like a channel called Ron Munitz. I will probably upload the recording of it here also, and I'm not a marketing guy, and I'm not going to say, hey, follow me on Instagram and all these kind of things. Like, if you subscribe, I suppose you get notifications. No hard feelings if you don't, okay? And so I will send a link later. I think then there might be like a link for this also. And it has some nice videos, okay? And they explain some things. Not very professionally edited, but they don't hurt, okay? Some of our customers, and let's start with the beginning. Some of our ventures, we do all kinds of things. Those who are interested are very welcome to contact me. And let's start with this talk. So the idea here is that we're going to take a Linux system that you have set up. And those who already seen a variation of this talk, please don't let yourself get bored. And if you have not done these things, it's a good opportunity to actually go and do. You will also have like time, you know, to like fetch the kernel, download and do all these kind of things when I'm explaining some things, all right? So we start with any Linux distro. You can build your own distro and use it. In this case, we use one of the Ubuntu latest LTS. There's going to be a new LTS in a couple of days probably. And we install these packages. Now, what the source code that I'm presenting for some of the things is going to be in this link, all right, at the top. And I suggest you follow the terminal and some things that I show. I will try to make it not too long, and I will give other sessions that will continue this one, okay? So let's go. First, I would like to talk to you a little bit about how to start your Linux distro. So in order to have a Linux distro, you need to have a kernel. Now, there are all kind of saying, okay, in order to have a kernel, you need to have like a computer, or you need to have a device. In order to boot the kernel, you need to have some boot ROM, some bootloader, something that will actually load the kernel into some place in memory, and so on and so forth. We do not address this now, as per this talk. What we're going to assume is that you will be using QEMU, okay? So QEMU, you will provide it the dash kernel parameter, and this will take care of your BIOS and one of your bootloaders, okay? You will provide it a kernel, you will provide it other things that we will discuss, and you will have your distro, okay? So we're going to start with getting the kernel. So the first thing you want to do is to actually go ahead and go to kernel.org, and over there see what is the latest version that is like available. So I'm going to now go kernel.org. I see that the latest stable kernel is 5.6.2. It went out a couple of days ago. We can see that there is another version of 5.5 that is still being maintained. This is like the 15 revision of it. And we see a couple of long-term, like 5.4.30, 4.19.114, 4.4, 218, right? And 4.9, 218. Pretty, like, there are a lot of revisions here, right? So, like, those who have been in my course that we did in Israel a couple of years ago in 2016 in Hanukkah, or like in 17, then it was one of the days that it was a day that 4.9 kernel went out. So it was like millions of years ago, right? So you're likely to see this number a lot if you, for example, use Android, okay? Now, if you design a device and you want to run kernel on something, you're likely to want to use a long-term kernel, so a long-term support. So in order to see like how much is going to be supported, you can look under the releases tab, and here you can go ahead and see that, for example, 4.9 is going to be supported until 2023, and 4.14 until 2024. And 5.4, the first kernel that is long-term support from revision 5 is going to be only supported until the end of next year. Okay, so there is no like a linear advancement in the end of life and of the version. Okay, there have been some the decision what is going to be like really long-term support with kernel, and this is like something a little bit different. So if we look, then you can see that if you check kernel.org every once and then, you're going to have an RC version, which means a release candidate. For example, when the stable kernel was 5.1.7, there was work on 5.2. And this guy was on release candidate 3, which means that there has been 3 iterations of testing of the new kernel that will be 5.2 after a couple of release candidates. Usually they're going to be about 6 or 8 or something like that. You can see same story, for example, in 5.2.9, and there is not always a release candidate. So last week, 2 weeks ago, there was a 5.6 RC7, and a couple of days after that, there was a 5.6, which is currently the latest stable kernel. 5.6 had 2 revisions, 5.6, 5.6.1, 5.6.2. It's actually 3 revisions. I think somebody's trying to join, so let me get him in. Sorry about that. And basically, sorry, we're in the meet, so it's like there's like context switch. Okay, context switch of people takes more time than of like the kernel to user space from process to process and so on. So we can see that we have those RCs, and if we want to get a particular revision, then we're going to either download it, like download a tarball, an XZ, a targz from kernel.org, one of its mirrors, or we're going to use Git. So if I go and do Git clone to a tree, and the stable is a table tree, there is also like Linux tree, there is a Linux Next tree. Git workflow is a little bit different than what you know in other projects, but this is like the source, okay? This is what Git was meant for, to work with the Linux kernel initially. So we can go ahead and get the stable tree. In this particular talk, I will not talk about this too much. Those who are interested, ask me questions, and I will answer all of your questions. We have time. And otherwise, I'll do it like in another talk. And we can see that if you don't want all the tree because it's going to be over 2 gigs, you can just do a shallow clone. So for example, I could go ahead and say, hey, I want 5.6 RC7, or I want 5.6.2, which is the recent one, --depth1, and I could get like the current tree or the corresponding tree, either from Linux, from stable, or from whoever, okay? I can go and do all kind of Git commands in order to see the remote tags, in order to see what is the recent kernel version without going to kernel.org. And what I can also do is I can just go ahead and do any Git trick that I want and know. So what are those stable versions, release candidates, and so forth? How is the development going on? Speaking of versions, then let's say if I was like right now in 5.1, then there would be all kind of release updates, right? So there's going to be a major, minor, and patch version, and these are going to be, they are going to appear in your kernel under, if you do head to make file of your kernel, then you're going to see what is the version that you're like currently on. And once you have a stable kernel, there are going to be revisions for it. Usually, there is not going to be any update for kernel versions that is like before it, if they're not long-term support. So maybe there's going to be just one. If you're 5.1, maybe there will still be new stable version for 5.0, but it's not guaranteed. And it's very unlikely, unless it's long-term support, that you'll have something for a previous version, okay? Now, so they progress, but there need to be happening something between this version and like the next one. So what's happening is that there is like a new tree, another tree called Linux Next, where new features are proposed. And what gets in the next version depends on something that is being decided on, something called a merge window, that once there is a merge window, after it's about 2 weeks, then after a couple of weeks, then there is like a freeze, so-called freezing of like the next version, that's going to be called the new release candidate. So if we were at 5.1, there is 5.2 release candidate 1. After a couple of release candidates, we're going to have then 5.2. So when we want to, let's say that we chose the kernel that we have, let's say that we know how to build it. Let's say that we got a recipe, and the recipe is going to be a .config file. It will be in your kernel tree, and we want to actually go ahead and boot it. So we need to understand like the protocols of the bootloader and how exactly we want to boot it, okay? So on PCs, you're usually going to use grub. On embedded stuff, we're usually going to be using a uboot, but there are all kinds of variations. And no matter what we want to boot, the objective is to actually go ahead, load the kernel to a memory, load perhaps something called a RAM disk, give it all kinds of parameters, and load perhaps something called device tree blob that will tell how the hardware looks like. So I will not talk about these things here. If there is like a request, I'll talk about it in another talk, and I talk about it in my embedded Linux courses. But in x86, then you have like a bootloader. It depends like on the framework. If you use like EFI, if you use legacy BIOS, if you use whatever, and the bootloader is going to be called. It's going to be listed in some particular place on your disk, perhaps. Okay, like if like you're on a PC, it's going to be jumped to, and then there is a very well-known like language in order to actually go ahead and load the kernel and provide it the parameters. So we're not going to cover it now. But the de facto bootloader in most like distros is going to be grub. Now, when we use QEMU, yes, we can definitely go ahead and load grub. We can load it in several factors. We can load it in the form that like you usually have these days, which is going to be an EFI application, which is those who like Windows or like to research like security. It's a P, it's a portable executable. There are very well-known ways to build it. It's not hard. And you can go, build grub, and actually boot it from QEMU also because it supports it. Just so you know, you can also boot uboot from it because it supports it. Like you just need from QEMU to boot something. You can also replace the BIOS, but we're just not going to get into it. I'm saying these things for the sake of completion. So what we go after we actually boot it, what's going to happen is that we will load a kernel. Now, when we talk about a kernel, the idea is this. There is going to be an architecture-dependent code, and let's go and see that. This is my kernel tree after I check it out, after I clone it and check it out. And there's going to be a lot of architecture-dependent code. I hope you can see my terminal under the arc directory. Okay, so many things are going to happen there, including the bootstrapping of the kernel, including the decompression of it. So when the kernel starts, when everything like starts, the bootloader or whatever loads you needs to have a start address, just like when you run like an ELF or whatever binary container you like, you need to jump to some address, okay? So this start address is going to be very, very, very architecture dependent. It's configurable, but what you do there also depends on architecture. For x86, for example, you start on real mode, where there are a lot of things that are a little bit different from what you know, and it makes it also a little bit challenging to debug with QEMU, for example, but it's super possible and it's not that hard. For ARM, there is no real mode and stuff like that, but there's architecture-dependent code that's going to do all kinds of things. One of the things that it's going to do is, and you can look at it and search for example, ARC let's choose like ARM boot. Then there's going to be everything under compressed, also in x86. You're going to have things like pg, okay? You have your loader script. You have all kind of headers. You have the compression code. And what's going to happen there is those of you who happen to run kernel instance in the past, then you'll see like the decompressing kernel message, okay? There are all kinds of things that happen in the kernel. Those who ever use like booted the kernel with VGA equals ask, for example, parameter, and x86 in order to ask what is the graphic mode that you want to boot, then surprise, surprise, it's actually also implemented in the kernel in x86. I'm not going to get into it right now. So there is a lot of architecture-dependent stuff, and that architecture-dependent stuff is going to decompress the kernel. For example, if it's like zipped in particular format, like GZ, like XZ, like whatever, it will decompress it, copy it to a place in memory that it will later jump to. And once it jumps to things, it will do, again, architecture-dependent code. And then it will go into this guy. So it's going to be main.c under init. That will have a start kernel function. That you can see here several things. You can see underscore init, which means that at some time, this memory that the function occupies will be released, okay? And you have ASM linkage, which gives pretty much an indication that it's going to be called from externally, okay? Speaking of like calling conventions and things like that, okay? So I'm not going to talk into it too much. I'm deliberately just going down, but giving you time to just read the name of the functions a little bit, okay? But it's going to do a lot of hardware-dependent things, like taking care of like interrupt handling and so on. And it's also going to do software-dependent things, like taking care of C groups, for example, okay? It's going to take care of the command line, store it somewhere. It's going to take care of the LSMs, those who know, Linux security modules, doing all kinds of things like this. And it's going to tell you things like what is like the command line. So those who already have Linux experience, they know Linux kernel experience, they know that PR notice is essentially a macro that encapsulates print K, okay? So it will do a lot of things like take care of the file system, like take care of the memory, take care of the tracing, take care of the scheduling, and so on and so forth. And at the end, it's going to call arc call rest init, which is architecture dependent. This particular function is relatively new. When I say new or relatively new, I mean like, okay, it's something that like hasn't been here 5 years ago or 10 years ago, okay? So this guy here is going to do all kinds of things, but mostly it will start a kernel thread called kernel init, another kernel thread called kthread-d. And this kernel init, long story short, is going to go and essentially do an exec-ve in user space, okay? So if we see what this guy does, then it's going to do, it is Israel, so a lot of people like security. So this is like, for example, where you mark the pages as read-only. So you can go, if you want to subvert it, you can go ahead, figure out what it does, right? For example, what control register it takes care of and which pages are marked like as read-only. And you can go ahead and do like the reverse thing, all right? You can do all kinds of things like that. And what it's going to do is free init mem. Remember that I promised you that something that is prefixed with underscore init is going to be released somewhere. So hey, here the memory is reclaimed. Congratulations. So back to what we want to go and do. We want to have minimal Linux distro. So kernel is great. We already covered that the kernel is booted somehow. It extracts itself somehow. It runs some code somehow. This is great, but not what else? What does it do more? We want to have something like a shell, right? I want to be able to open a new tab and do ls or ps or I don't know what, or exit for the sake of discussion. So what I'm going to do here is actually go ahead and fork an exec-ve, some process in user space. Now, just have a look at the code. You will see some well-known path. Has been init, that's init, bin init, bin sh. And if nothing works, it will say, hey, no working init found. Try passing init equals option to the kernel, see Linux documentation, and so on. Okay. So if I go ahead and just show like an example of it, then we'll show you. I will cheat. Okay. I will do the no graphics, and I will get rid of this line. So I run all kind of things. These print are deliberate because I thought of showing something with the graphics. And here is this message like, not syncing, no working init found. Try passing init to the kernel, see Linux documentation, and so on. Great. So now I'm going to do Control A, and then leave Control and hit X in order to get out of QEMU. And we have some indication that the kernel works. Now we need to do something in user space. So this something essentially is going to be loading an elf or a script. I will not go over it, but when you have the shebang, then there is something in the kernel itself, something called bin format _ script. It's under file system directory that enables you to parse the shebang and then execute what's after the interpreter. So if you have bin sh, then it's going to execute the elf of bin sh. If you have Python 3, then it's going to do this, and so on and so forth. So we need this one binary or script that will start our entire user space. So here you see me in Chrome, you see me sharing graphics. I do a lot of things. I do it in user space. So this guy is going to be, if you do, for example, PS or PS3, right? It's going to be the first one. And in modern distros, it's going to be systemd. So if you have like a dependency tree, and what you have, if you just do PS, you're going to have this guy that is 1. So it's going to be PID1. And if you remember when I showed like the kernel code, then I also showed that it started two threads, one for init function and the other one for kthread. So this is like the second one. Every time you see a process with a name with squared brackets, it means it's a kernel thread. All right? Good. So we need user space in order to create something. And the main takeaway that I always say when I do these kind of sessions or when I do any kernel training is that you need to have the kernel working. And once you manage to get anything in user space working, then you're good to go. You will know what to do or will help you to do whatever you need to do. But the problem is completely separated. Kernel is kernel. And the moment you are able to execute one single thing, like write something to the terminal and then blink a LED or run systemd, parse init files, then you're good, you're done, and your kernel work is done until you need to have like a new driver, until you need to do all kinds of optimizations and so on. So I emphasize it, and I take your time to emphasize it, because from this moment and on, for example, if you have like systemd init, if you have BusyBox, the Swiss knife of embedded Linux, if you have Android, if you just have your own script, then it's legit. Linux is Linux underneath, and that's it, okay? Now, in order to actually execute this init, you need something called a rootfs. Now, I actually want to tell you, to give you a little hint to something that I also like doing. By the way, there's somebody joining. Is the pace okay? Like, are we good? We're not bored? I can go much faster, like if it's boring, right? Okay.
I think it's good.
Yeah, good. All right. So basically, what we're going to have is, this is just a little cheat. What happens if you don't have init rumfs at all? And this is something that a lot of people don't know. I'm not going to explain it too much, but it's good to know. Under the user directory, you have these files, okay? Now, these files are going, and just look like at this script here. Then init rumfs, sorry. This little script here, okay, is going to get all kind of parameters that it can create. For example, symbolic link, for example, directory, for example, node, pipe, socket. And it will generate a template for either a default init RAMFS, so that even if you do not provide anything else to the kernel after we just build the kernel, and I'll explain what init RAMFS is in a second, it will have some initial root file system that looks like this. We'll have dev, it will be empty, that will have dev console, which is a character device with major 5 and minor 1, /root, and the dev console, as I said, okay? And of course, you will have the slash file, like the root. So even if you don't have anything, you will have a very, very, very minimal root file system. What is root file system? Somewhere where the kernel or the resulting user space application can look for all kinds of files. You can then, from this, mount other file systems, and then you expand like the tree as you would have in your distro. Now, a very nice way to examine it and prove yourself that it's true is doing something like creating a RAM disk, which I'm going to talk about soon, with a simple executable written in C, okay, but compiled statically, that will just do, for example, the implementation of ls and stat, okay? So you're going to do read dir, you're going to do stat, those system calls, and you will see that even if this is the only thing that you have, this init file, you don't create any directories, don't mount anything, you will see it. What you can also do is provide other templates for creating like the initial RAM disk and baking it into the kernel. Why do I mention it? Because essentially the initial root file system is going to be referred to by well-known place in the memory. You need to load it somewhere, okay? So you can either do it as part of like the kernel build process, or you can add it yourself. Now, how do we add it, and what is the motivation for that? So the motivation is that we need to have somewhere to address files in, to be able to do things like open, read, write, and the like, and all the system calls that we like. And in order to do that, then we need to make the kernel aware of its existence and how to get it. Of course, I also need the kernel, especially if it's like a physical device, if it's not just in memory, like in the RAM, to be able to work with the physical device. I mean, it needs to work with the particular hardware. It needs to support something called block subsystem, and it needs to understand the data over there. So the objective of a file system is to let the kernel know like how to handle the data. And the objective of the file system, as far as the user space is concerned, is to be able to give nice names and all kind of things like that, that we all know. So what will happen a lot of times when we go and have such an initial file system is that we'll have very minimal file system in memory. And from that, we're going to pivot root or root or switch root to the root file system, for example, the one that will be in our disk or wherever you want to have it, NFS or so on. I was delayed a little bit because I don't want to repeat the exact same things I said in the talk last week. All right. So I'm doing things a little bit different. Like if you notice, and focus on some other things. So I will not extract again the data in Ubuntu. Just believe me when I'm saying that it's like this. The other talk is also recorded. And of course, ask me questions and I will answer it. So the init RAMFS itself, usually the idea is to mount the root file system, but it can serve as the root file system. Nobody told you need to share root or switch root or pivot root, okay? So there are several formats that are supported by the file system itself, by the init RAMFS. And what you need to do is to select the required compression. A lot of time it's going to be just CPIO or CPIO compressed with XZ or whatever. What you're going to do over there is actually put like your initial executable, and then as we saw in init main.c, rest init, and we're going to, sorry, we are looking for arc rest init. So we're going to look for the kernel init function, and this fellow here is going to do these things. If it has a rumdisk execute command, that means if it has something like rd init, looks like this, rd init equals some path, all right, then it will execute it first. Now, otherwise, if there is an execute command such as init equals whatever, then it will execute it also, okay? Otherwise, its default is to look for /init, and if this doesn't work, it will try sbin init, etc init, bin init, bin sh. Now, what is this try to run init process or run init process? I'm going to make a very, very, very long story short. So this guy is going to be calling do exec_ve. That, as you can guess, is pretty much doing something like exec_ve. Take a minute to, okay, 5 seconds to familiarize yourself with it. So you have like an init file name, and get name kernel actually translates it to its handle in the kernel. Kernel doesn't speak file names, okay? It speaks other descriptors, and you have here argv and env. Looks very, very, very familiar, okay? So once we run this /init, then everything is good and everything is great, and we can take care of our file system. So here is, for example, I'm not going to get into it too much, the Ubuntu, like the one that I'm running now, boot process. We have like EFI. It's going to have a grab application. It's going to load the kernel in init rumfs. We're going to have the parameters in grab. The kernel is going to be boot, and the init rumfs is going to be provided to it. It will run init, which will be a busy box. If you unpack, as I have like in this slide, unmake init rumfs, you will see that under main you will have like busy box, okay? And this busy box will actually go ahead and do switch root. Yeah, question? Is there any question? All right. Another question. All right. Okay, so so this is like the first part, okay? Now, it is taking, I have the time, I just want to see like what interests you and what not, right? This is pretty much the meetup, the coordination of time is my responsibility, so I allow myself to do whatever I want, right? But I just want you to not be bored and to be interested, okay? So the second part is taking this theory and actually making something with it. I can do it in 5 minutes. I put so much materials like in this GitHub and so much explanation in the commit messages that you can make sense of it. But there are some trickery over there. Okay. So the second part is going to be QEMU. So we're going to go and boot this kernel and around it that we will create using QEMU. Okay. We will skip now kernel debuggers. I can talk about it later. And for the hardware debuggers, actually not yet in QEMU, I actually put a video in my channel. I will show you later. Just look like for 1 minute. That a series of video that shows like with a computer and like a super old laptop, how you use KDB and KGDB and all kind of like annoying things that you will run into. Okay. So with QEMU, things are always easier. But let's just talk about the software now and not about debugging. So on the GitHub repository that I posted, we have several scripts. These scripts: fetch, build, busybox creation, and run kvm. And I will now explain the rationale behind them in 1 minute. In order to build the kernel, I don't need to do too much. I can go ahead and change directory to my kernel source. I need to somehow create a recipe, a configuration file, .config for the kernel. And I go through a lot of trouble into proving what is like the real minimal one, but to make things easier for you and see that things actually work, then what you'd want to do is just say, okay, I want to use the def config, all right? And this, if your architecture is x86-64, it will create a def config for x86-64, okay? Now, if I want to add all kind of Virtualization stuff, I'm going to also use kvm config, not really needed, and then I will build the kernel. That's it. At the end of it, I will have a VM Linux executable, and I will have a binary under arc, boot x86, busy image, because this is the default. Now, if I want to have this RAM disk that I talked about, this initial file system, I'm going to get BusyBox. Okay, this is a typo. This should be 131. I will change it. Because I upgraded the version. I'm going to go and get BusyBox. I'm going to configure it. Now look what I do. I don't think, I'm not thinking too much. I just take the default configuration, but I configure it as static. Why? Because otherwise I need to take care of having the corresponding libc, and I need to have a sysroot, and I need to take care of dependencies. And for these things, long story short, you need to have a build system, okay? So this is not the case right now. I'm going to make some initial directory structure. As you can recall, dev console will be anyway, and also /root, even though I do not create it here. And I'm going to populate the init script or populate the init executable and do all kind of things. Easiest thing to do is to do whatever I do in an init script and then exec bin sh, that as you will see is actually a link to BusyBox, okay? Now, if I don't run with an initrd, you will see the kernel panic as I showed you before. And if I do run with the init, then I can actually go ahead and start my things. Now I can populate this RAM disk by, for example, installing kernel modules into it. So it's really nice. I can do, I'm not talking about modules now. If there's interest, I will teach you maybe in the next hour to build kernel modules. I can go ahead and make install into the particular directory, for example, into the RAM disk, and then I will have this layout, okay? Here are KOs, just as I expect to see them myself. So after I do that, if I did something like that, I would want to make sure that I update my RAM disk because it has been packed. So I can also build out of 3 modules. I will skip modules in this talk. I can merge all kind of configurations, but I will skip it also in this talk. You just need to know that you can take very small configuration snippets and create the kernel configs from there. And you can actually go ahead and just work because you have like a kernel and a user space that work completely. I apologize a little bit for the delays. I just try to remember on the way what I talked about in the previous one, because I know that some attended, and not to repeat the same things. And because I already said that I will do a session of several lectures, so we'll have time to cover everything in any depth that you want. I sort of teach kernel internals and build systems and Yocto for a living. So, I can do it for fun also. So far, we need to build several things. We need to get a kernel. We need to build user space tools. We need to pack the RAM disk in order to have this initial root file system. But what if I also want to take care of dependencies? For example, I want to just go ahead and make ls that I built and relies on shared objects, like on dynamic libraries. I want it to actually work. For example, if I see who is ls and I do ldd bin ls on my host, then it will have on itself dependencies. Any of you that ever build an embedded build system and try to just go ahead and build on one place without correctly updating the libraries knows that you will usually not even get an error. It will just say, hey, can't execute something, and you will not even understand what the hell it wants. So what it wants is to run a linker, because when you run a file, you actually run the dynamic linker, right? and the dynamic loader. So all these kind of things you need to set it up, and it's not so easy. So in order to do that properly, you will want to use a build system such as Buildroot or Yocto or any other thing that you want, okay? Now I'm going to teach a Yocto project course in a couple of weeks, two of them, one in Europe and Israel time and the other one in United States time. You're welcome to ask me if you're interested in Yocto project, and you're very welcome to register. Now I also put, if you don't know what it is, I put a couple of videos in the YouTube channel as well that explain something, okay? So speaking of build minimizations, I'll not talk about graphics now because I want to give you time for a break, and I want Omer to give his talk. So I'm going to talk a little bit about what is the way not to start from building the default and then trimming down, but the other way around, okay? What we want to do is to minimize the build. So the idea here is going to be to start from nothing and build up. And the very basics are going to be, of course, very hardware dependent, but the minimum I would want to have is actually see something and be able to type something. And this is called having a console. So a console can either be via a serial line. So I think I'm on camera, and I was doing some videos. So this guy is a serial line, an ancient one. Over there, like if you see, I have a lot of other serial cables that I can actually connect to the BeagleBone, to the Dragon board, to Jules, to whatever. And what I want to have is either console that is input-output on a serial line or on the screen. Now, on x86, everything is very, very, very easy because the BIOS implement a lot of functionality. If you just run, for example, QEMU, let's say, let's just give an example, although I don't intend to do it too much. So QEMU, and this is going to be the kernel, okay? And for fun, I'm going to say VGA equal ask, okay? And I will get rid of the other console. I was supposed to do here append. The no graphic was a mistake, of course. Yeah, so look what I have here. I hope you can see, like booting from ROM, enter to see video modes available, space continue. And this thing, I promised you that the kernel actually implements it, okay? But if I let go and do all these kind of things, or do like scan, or just choose one like at random, okay? Like let's just put E, then you see this guy here, like it's very, very, very small and so on. But I actually have here like one part of the console that is the output, okay? I also would want to have like an input, but in order to actually do something useful with the input, I want to either enable a debugger or listen to some key events or have a user space that, for example, executes a shell, okay? So one option would be like a console that is keyboard and like screen. The other one would be serial. Very, very, very important. On x86, simple demonstration that I did was possible because the BIOS implement graphics and the BIOS implement getting input from keyboard. So it's very easy, okay? We're not going to talk about the drawing path now, and we're not going to talk about graphics. I'm just going to talk now about monitor and keyboard console and serial console, but this will wrap up this particular talk, okay? So for example, we're going to focus on QEMU that has these BIOS, C BIOS, and serial interface will be via TTY S0, and the screen is the default, okay? Now, here are several ways to actually decide what is the hardware that I provide. So the first one is going to say, hey, the video that I want to have like a virtual frame buffer. You will not see anything with it, but you can record into it, okay? You can record into it, and test video, test graphics if you want. VGA ask will ask for the modes, as I said. I can go ahead and say, I support VGA equals this parameter. It's one of the VISA modes. But the console, that is what's going to first be my interaction with the user, is going to be the serial one, okay? I can actually provide several console parameters. Only the last one will be like the real console. How do you know like what the console is? I'm not going to do it because I will lose like the graphics, but you can go do the TTY command, and then you will see dev console, for example. All right. So when you do this is like another way to add it. And you can, for example, have only serial, no graphics at all, by providing QEMU with a dash no graphics device. But you must provide it in this case. You must provide it with the console equals TTY as 0, for example, parameter for QEMU. It's very, 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 very important, okay? So an example, for example, for like the serials would be, here I attach 2 serials, check it out. I'm telling you this one serial is stdio. If I do stdio and note mon colon stdio, then Control C will terminate also QEMU. Otherwise, it will not. And the other one serial file, this is my serial, actually means that if you go and, for example, from your target QEMU, write in this case into dev TTY S1, they go by order, then you will see the output in this file, okay? So for the kernel itself, you will need to actually set up these things to work. Serial console doesn't come for free. You need to actually define it if you start from nothing. So the way to start from very minimal things to add the features is to know what you need to add. And here I'm saving you some time. And you have a lot of information about it in the commits in the repo that I posted. And I will talk about it in the next talk if there is interest. So we start with all no config or tiny config. The difference between them, the main difference is the tiny config aims to optimize the size, and the all no config just says no for everything unless it has like a default value, and then you stay with the default value. And what you're going to want, for example, to see messages in your console is, first of all, to have a TTY. TTY is from input output. Then you want to be able to have print K, assuming you want to see kernel messages. You can live without print K and it will be perfect as long as you are able to actually start user space, or you're able to connect the debugger to the kernel and see some things. Otherwise, you will not see nothing, you will not see anything, and you will not know what's happening, and you will not have like an indication of your progress. Now, to see kernel messages and like to have like a shell and like to put some things, you're going to see it on the screen, you need a virtual terminal. For serial, you don't need it. So these are the configs needed for this, VT and VT console. In order to see some things on the screen and have like graphics, then you need some driver. So VGA console is like the easier one. And for the serial, you're going to need to define a serial hardware. So we're going to use the 8250, and you need for that the driver itself and the console driver for it. Okay, you can learn all kinds of things by having proc TTY driver serial printed. Now, this keyboard is not for the serial, only like if you want to have with the screen. So these are the things that you want to do to have a console of screen and keyboard. And to have user space, you need to be able to process the initial RAM file system. So there are 2 things you want to have there. First of all, you want to even be able to run anything. So ELF doesn't come for free. You need to config it. You need to say that you support ELF. And executing a script with a shebang also doesn't come for free. You need to specify it. Okay, you don't have to, but you can. What you also need to do is to say what is the compression of the RAM disk that you want. And then once you've done these things, you want to have a useful user space, like to have /proc, to have /sys, and all these kind of things. If you don't have proc, you can do PS, right? Because PS is going to parse proc, for example. So these are all the kind of things that you want to do, and you add to it, and you add to it, and for the BugFS, you add to it, and it has no end, okay? So like at the end of the procedure, you're going to see this is like in a screen. I will show not in a screen. I will show like in a terminal, something like this. And so let's do, I want with the RAM disk actually. So I'm going to run here something, and this actually got printed because my minimal RAM disk had something like this. So I did this. I mounted proc because I configured it into the kernel, mounted sysfs, mounted debugfs, So now I can use ftrace. Now I can do kprobs. I echoed this thing in color. I did auto enumeration, like UDEV, if you know it, of my devices. Okay. I enabled here dot plug system, although I don't really need it. And here I did export env equal ron to an environment variable, and exec sbin init. What is sbin init? It's busybox init. So you could just as easily just execute bin sh in the master branch of the repository. This is what is happening. And sbin init, one of the things that it does is actually, first of all, it is within exec, is within the same process. It's going to be PID1. So the environment variable, it remains, okay? Now, init is going to parse something called etc init tab, okay? And this guy will have like a particular format. So I'm not going to get into these things here. If I have a graphical thing, I'm actually going to show here a splash screen, showing the PSCG and showing myself and some progress bar. And I'm here going to open a shell in TTYS0. And the shell is going to look at the environment variable. And it's going to see, hey, what is env? Env is ron env. So what do we do in ron env? So let's have a look at ron env. In this case, ron env is going to have this ls. I'm going to put a prompt, you see. This is why I have this red thing and the folder and so on. And I'm going to cut extra banner. So this is an example of like a root file system that I did, but I can do like so many things. And I can here have systemd, and I can here take any root file system that I want from a container. A lot of people will say, hey, we like containers, we like Docker, we like LXC, we like containers, Docker, 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 Docker. So you can go and take the files from where it is stored in a Docker, pack it somewhere, change root into it, and that's it, okay? Or like run the init from the Docker as the init, and that's it. Like, and then you have like a fully fledged Docker image in like wherever. So this is actually a neat trick for people who have the possibility to run QEMU, but they have all kind of problems with WSL in Windows. So you can say, okay, I'm not going to start VirtualBox and insert like an entire machine and so on. I'm going to have a very minimal system, and boom, I'm going to start like my Docker, okay? So these are all kind of things. And with this, I want to give you time to take some break, right? And I want to give Omer time to prepare his talk and to go on board. Omer, are you with us?
Yes, actually, I have a question about your lecture. When you enable a serial driver or some sort of input, don't you need to specify the address of the controller? I know it's done in the device tree, but you didn't include it.
The baud rate and topics? Yeah, so that's a good question. Essentially, you do, but when you're like in QEMU, that you don't need too much. I mean, there are always defaults, and the defaults are friendly. Let's say this, okay? But usually you would want, and I put like on YouTube a couple of lectures on working like with serial. Like I can go and take it like another step forward. Like what we can do is say like, hey, like if I have like real hardware, I even know the baud rate. So like a lot of times you just need to go with like a logic analyzer and echo some things over the terminal and try to figure out like the peaks, like to see what is like the difference between like two peaks, and like, you know, put like a cursor or something like that, depending on like the analyzer that you have. And then you would see, okay, this is roughly 115, 200 baud, so this is what it's going to be. Yeah, so I will conclude. Are there any other questions? Because I'm concluding here, okay? There are other things I will proceed in the next time, okay, if it interests you. I'm just going to say that it's very, very, very complex to get everything like aligned, especially like with the root file system and so on. So for this, there are build systems, and please feel free to ask me questions. The objective is to get from a host into a target that is like working. I will not cover it now, I will cover it in the course that I have actually, it starts next week, one course, and the other course starts 2 weeks from now. And you can go ahead and look in this playlist. There is a link here. You can go ahead and see a couple of lectures on Yocto project, especially like the lightning talk, which is super short, like about 15 minutes, and then actually explain more, like how I build the lightning talks. So I like to give a lot of information, and I did it. And my next public courses that are going to be given online are here. All our subjects like to a minimal number of attendees. The second Yocto project happens for sure, like this one. And if you want to, as I said, if you want to like go and take like an Linux Foundation course, then please feel free to reach out to me. Even if I don't teach, I will give you a nice discount. And I'm very happy to get like any questions if you have. Okay. So that's it. I will.
Yes.
I have a link for it on Twitter. I will put it in Twitter and on Facebook. And like, let's put the link here. Yeah, I'm listening for questions.
Are the slides online?
On LinkedIn. Yeah.
It's like the usual question.
Yeah.
Are the slides available online?
Yeah. So they are. So please look. Like I put it like on Twitter, like about last week. It's like the same link, and I will post in an organized way, like in the Meetup group or like in another place. Like I'll send you like an email, like with the slides of everyone, with summary of everything, and with call to action, like for the next meeting. Okay.
Okay, thanks. It's great.
Okay. So I hope you had a good time. All right. And I will do like whatever you guys want as per my. It's very important for you to okay. Now somebody please somebody needs to mute whoever is around. So what we're going to do now is this. We're going to take 7-minute break, okay? And after that, Omer will give his great talk about hypervisors in ARM. All right? So I'm going to put the timer now, and I'm open for questions, of course. Like, I'm still here, all right? So.
My question is only half related. It's not so related to the minimal system, but it is related to a minimal system on Intel. I'm not sure that you, if you guys recall, but like I think it was like 1 or 1.5 years ago, Andreas Tenenbaum sent a thank you note to Intel because apparently his Minix operating system is the widest available.
Yeah.
Do you know how or when it's initialized and how it's initialized and why it is on all Intel platforms?
Yes, but it has nothing to do with Linux. Okay, so I do know. So the idea is like this: like you have several levels of operation, like in Intel CPUs. So apparently, what you have is a level that is like available even if like your core 0, let's say it like this, is shut down. Okay, so they have a micro OS that actually is used for provisioning of a system that you can do all kind of things remotely and so on and so forth. So it happens like completely regardless of your operating system.
It makes sense, but it's also, by the way, something that happens on the Raspberry Pi, for example, because the Raspberry Pi, as far as I know, have like the initial bootloader is actually coming from the GPU.
I actually am not aware of it. Like I'm happy to hear more. Like what I know usually, like in ARM, I mean it depends. I mean when you have power up to a system, then it really depends like what you run. Of course, you can have like a different cores or like different even like different packages, different thing, and you can execute them in parallel. Like I have no idea about Raspberry Pi. Usually when you have like ARM systems, then ARM-based system, then you're going to have, actually I'm pretty sure Omer is going to talk about it, but you're going to have power up, and then there's going to be some boot ROM that will get somewhere. Now it depends what you license in ARM, like whether you have trusts on, whether you have a hypervisor, and so on. And it's going to go like to the highest exception level, and it's going to like L3, and it's going to boot like all kinds of things. It's going to boot the other cores if there are, and so on. Now, if you have, I'm happy to hear like about a Raspberry Pi. I mean, maybe you can give a talk about it. It would be nice.
It's a very short discussion. It's not something that you can make talk maybe even 5 or 10 minutes, because there's the Raspberry Pi boot sequence, which actually I read about it. Yeah, it's not something that I'm an expert in because I'm not that familiar with Freescale. No, it's not Freescale, it's Broadcom, sorry. But basically what I understand is that the GPU is first initializes. And by the way, if you've noticed, if you ever started Raspberry Pi and, for example, you started it with like 2 amperes, 5 volts power supply, then often you're going to see low voltage. And apparently it's not something, it's like this kind of lightning picture. And apparently it's something that came from the Linux kernel. It's something that comes from the outside. It's something that comes from actually from some kind of external process that runs in the Raspberry Pi in the Broadcom system. And it's one of the proofs. This is why I don't like a lot of things running on the Raspberry Pi, but because something can actually take over my system. Apparently, it can take over the screen, it can take over other parts. This is why I find the Raspberry Pi, for example, not such a safe system, unlike, as far as I know, BeagleBone, which I didn't find anything else that actually takes over. As far as I know, BeagleBone, once you start it, the bootloader goes in.
Yeah, so this is true. I'm part of the BeagleBone bird. The thing that's not about the Raspberry Pi is the bootloader is GPU, so the video core boots the Raspberry Pi, and the video core, the bootloader is proprietary, so it's a blob basically that gets loaded out to the video core, so you don't know what's happening. But most other boards, including BeagleBone, just the SoC has a ROM that then jumps into. So it's just the BeagleBone, like many other boards, is running upstream in boot. So the ROM on the TI SoC will then jump in boot, and then it's so the Pi is really unusual on the GPU.
Yeah, so Drew, we didn't hear you well. Nobody heard you well. I think if you can repeat pretty much everything that you just said, it would be nice.
I think I was on a bad, not a very good microphone.
Yeah, now you're good.
So what I was saying was that, the Raspberry Pi is odd because the video core, which is the SoC in it, it boots the GPU actually boots the system, bootstraps the system, and it's a proprietary blob. So the BeagleBone, however, has a TI SoC, which is kind of typical, where there's a ROM in the SoC that jumps into the bootloader, which is U-boot. So BeagleBone, like probably most other ARM boards, just has a U-boot. So that's nice because you can tell what's happening. But on the video core SoC and the Pi, it's a proprietary blob.
Okay, Omer, how is it going? Are you set for presenting yet?
Yes, can you see my screen?
Yeah, we can see your screen. I was dreaming of having like the timer, the countdown, being broadcast live. But I will fulfill my dreams at another time. There are 8 seconds left. I think you should hear like an alarm soon. Okay. All right. Thanks.
So let's start. This talk we're going to talk about a little about virtualization in embedded systems. How can we use it to our advantage to aid us in our design. I assumed that some of you know some of the elements in the ARM architecture, but if you have any questions, feel free. I'll try my best to answer. So my name is Omer Kaspi. I'm a system engineer at Gardnox. We are dealing mainly with cybersecurity in the automotive space. So I have experience in cybersecurity and in embedded automotive systems. I have some experience also in communication systems from the IAF. That's about that. So let's first start with a quote. This is a quote that's called the fundamental theorem of software engineering. Basically says that every problem basically can be solved by introducing an extra layer of abstractions, because sometimes we don't want to know how something was implemented. For, let's say, for example, let's take a hardware abstraction layer, for example. If I'm an application developer, I don't really want to know or care about how the driver for my hard disk is implemented. I just know I have an interface for it, and it does what I want. I don't really care. So virtualization, specifically in our case, we are talking about hardware virtualization, which is the act of virtualizing hardware platforms, for example, CPUs, IOs, for example, Ethernet, cards, and every other peripherals. We'll start with defining some terms. A hypervisor is a computer program that allows us to create and run virtual machines. Virtual machines basically comprising of a hardware platform and a CPU that can run in parallel on the same chip. We'll talk about that in the next slide. Basically, high virtualization or hardware virtualization allows us to run multiple operating systems on the same hardware, and it allows us to use multiple OSs it allows us to have multiple OSs use the same hardware. It allows us for hardware consolidation, cost reduction, because let's say we want to have a secure system and we want to have separation between different domains. I will tell you about, let's see, I'll tell you about, sorry, here's an example of such kind of system. This is an automotive example. Today in the automotive market, you have a unit which is called an IVI, which is the in-vehicle infotainment system. This is what you use for playing music and see videos, sometimes maybe to use Waze. And you have the instrument cluster, which shows the speed and the gas and things like that. And today, mostly the instrument cluster are mechanic or partly digital. And the IVI it's a separate system. Today, car manufacturers want to consolidate them and make them on the same ECU. And this creates a certain, let's say, interesting aspects, because now you want to be able to run your Android system or QNX or whatever operating system you're using, which doesn't have any constraints except user experience, and you want to run the instrument cluster and the tiltels that has safety implications. So one solution for that is to take an hypervisor and run both operating systems, one for the infotainment, for example, automotive Linux or Android, and another one for the instrument cluster, and have them both share the resources of the same hardware. Any questions up until now? Okay, I guess it's okay. So basically, this allows us to use this separation to ensure safety in this kind of system. So let's talk about how hypervisor types. We have mostly two, which is one is called type 1 and one is called type 2. The type 1 hypervisor basically runs on top of the hardware and spawns guest OSs. And one of them, which is type 2, runs on top of a host operating system like Windows, and it runs as a process. Type 1 hypervisor that you may know is E6i or OKL4 or Zen. If you know, it's quite common in the embedded place. It provides us better performance than type 2 because you don't have an host OS that transitions your requests, and it allows us full separation of the OSs. The type 2 one, as I mentioned earlier, runs on top of an OS, and common examples are VirtualBox or VMware and other kinds. So let's talk about how it actually happens, okay? So I guess you know a bit about ARM v8, but I will talk about it, and if you will have more questions, I'll talk about it. Basically, in ARM v8, you have 4 exception levels. The lower the number, the lower the privilege. So EL0 is where the application runs from. It has the least privilege. EL1 is for, in our case, the the guest OSs that runs on top of a VM, and EL2 for the hypervisor, which is sometimes called VM Manager. And EL3 is the lowest, mostly bootloaders and sometimes trust zone. So we in this presentation, we'll talk about mostly type 1 hypervisors, which will run on EL2. And it will have access in EL2 to all the virtualization mechanisms that ARMS provides in ARM v8. So, but in order to go from the guest OS to the hypervisor, because now you might need to have some kind of a service from it, you have what is called a hypercall exception, which is just like syscall. If you know it will be implemented, basically you have an instruction that makes the processor go from EL1 to EL2, and then it does some stuff. We'll go over it in an example of how to virtualize and console later on in the presentation. So let's talk about what we need in order to run an OS on a hypervisor, and then we'll deep dive to most of them. We'll need to be able to handle privileged instructions because in, let's say, I don't want to say default scenario, but sometimes the OS doesn't aware that it runs on the top of an hypervisor, and it might wanted to do some operations that are privileged. For example, enable layer 1 caches, enable MMU, so on and so forth. So the hypervisor need to be able to handle it in some way. Second of all, we need a mechanism to virtualize the memory space, because now we have both operating system on the same chip. We need them, of course, not to interfere with one another, as we need to solve that. We need to have some restriction of IOs, because that might have implication on security as well as usability. We'll talk about that in the next couple of slides. We need to be able to virtualize IOs in some sort of way, as well as interrupts and timers. Up until now, it's okay? Or you have any questions? Let's see. I don't know if you have something in the chat. No, it seems okay. So as we talked about, we need to be able to handle privileged instructions. What actually happens that when the OS executes the privileged instructions, what happens that the hypervisor gets an exception that tells him that it had some kind of exception with registers that helps him to identify what happened, and then the hypervisor can do, for example, let's say the OS asks for L1 cache enablement, so the hypervisor will get an exception and see, okay, we asked the OS try to enable the cache, so let's enable it if it's not enabled. Regarding the virtualization of the memory space, what ARM did in ARM v7 and some sort of an extension of ARM v7, sorry, I meant what ARM did in ARM v8 and on some extension of ARM v7. What happened is that they use two translation tables for the MMU. So basically, this is a diagram that shows how it happens. The OS configures the first stage 1 table, which is like you know from how virtual memory is done using processes. A process thinks it has the whole memory space, and it actually maps to certain RAM or peripherals or flash. And the hypervisor uses the second stage table in order to take this mapping of the OS into actual hardware. For example, parts of the DDR are actually physically mapped to certain OS and some of the peripherals, but the OS thinks it has everything. Okay. Also, ARM provides a VMID register in order to know which VM we are on. So so that the MMU will not mix TLB entries, which is some sort of cache for paging. Okay. About restriction of IOs, now let's say a guest OS wants to use a certain master on the bus, let's say a DMA or an Ethernet controller. It needs to be able to use the same addresses or the same physical addresses as the guest OS. So it needs some kind of translation. So what happens is you have a unit that's called SMMU, which is System MMU, or sometimes IOMMU, which allows this second stage translation, like we did in the MMU, in order for the guest OS to take the addresses it wants for example, the DMA to copy to, and just give it to the DMA. And the system MMU will use this in order to make the translation to the actual physical address. System MMUs aren't mandatory in some of the chips. I saw implementation that they didn't use it, but sometimes it's also used for security, because when you have a master on the bus which isn't a DMA, which isn't a CPU, you can actually intervene with the operating system functionality. Actually, there was a talk on Cross Communication Congress, I don't remember which one, but it wasn't the last one, that they showed that you can use, they took a board that they used without system MU enabled, and they showed that they can use PCIe in order to delete the password that used for entrance for Linux system in order to manipulate the OS so we can enter without a password. Just an example how you can use it as a security mechanism. Okay. Regarding virtualization of I/O, we have mainly three methods. We have one which isn't listed here, which is direct assignment. We can just take a device and tells the hypervisor, okay, this is the assigned for VM1 instead of VM2, and it's a direct assignment and no one else can use it. Of course, it has some advantages, but mostly you don't really want to use it. And you have full virtualization and power virtualization, which we will talk about now. In full virtualization, as I mentioned earlier, the OS doesn't aware that it runs on top of an hypervisor, and it's just doing the normal accesses to the hardware controllers. But the the hypervisor is configuring the MMU in a way that it will trap these operations and then emulate the hardware itself. So let's, for example, look at the diagram here. Let's say this app asks for a receive on a socket. This will go, for of course, using a system call to the kernel, then to the driver. The driver will try to access the buffer of the Ethernet controller. This will trigger a trap or an exception to the hypervisor. The hypervisor will actually do the talking to the Ethernet controller, and will emulate the operation to the driver. So in this case, the emulation and the Ethernet controller doesn't have to be the same model. It can be anything you want. You can emulate something that the OS supports, and the Ethernet controller can be something else completely. But this full virtualization, because of the emulation, has some performance penalty. But it allows us more flexibility, because we don't need our OS to support this hypervisor. It doesn't need to be aware of it, opposed to the second way we are going to present. The second way is called power virtualization. It's basically very popular on Zen. They actually really pushed it. What is done on power virtualization, when compiling the OS, we tell it it's going to be aware that it's going to run on the hypervisor. So for example, when I compile an a Linux kernel VM that's going to be run on Zen, I have some configs that allows the Linux kernel to be Zen aware. It knows that we are going to run it. So now, instead of trapping every access, the kernel knows we are going to run on top of a hypervisor, and it's going to use hypercalls in order to ask operations of the hypervisor, and then the hypervisor will catch them and actually do this operation. This allows us more performance because we don't need to emulate, but that allows us less flexibility because now the OS needs to support our hypervisor. So far, so good?
There was a question about, I don't know if you saw it, about if the full virtualization is hypervisor 1, level 1, or and the level 2 would be the power virtualization.
It doesn't matter, I think, because if I'm not mistaken, these are agnostic to the type of the virtualization. Type 1 and type 2 both can use these methods. For example, actually, in VirtualBox, I know for certain that you can use emulated and power virtualized network cards for your network interface for a Linux virtual machine, for example. I hope this answers your question.
Yeah, it was mainly just I see like other presentations where people say this is a level 1 hypervisor or a level 2 hypervisor, and I was kind of confused what they meant by that.
Okay, as I said, they probably meant that the hypervisor runs on top of the hardware or it runs on top of a host operating system.
Okay. Yeah. Right. Okay.
Actually, if you have questions, anybody, I prefer to do it using voice because I don't see the chat when I'm presenting. I have only one screen on my computer. So let's continue. Now we're going to do an example on how paravirtualization is actually implemented for a console on Linux, from Linux to the Zen hypervisor to see how it's implemented. This is an example from the Linux kernel. I think it's 5.5 or 5.6. I took it from Elixir. This is, of course, when you want to read from a console or write from a console. Of course, let's say the application use syscall to enter this stage. This actually calls, it will actually call the operation from the hypervisor. So here, if we will go to see this function hypervisor console.io, what it will actually do, that's actually a macro that will actually be expanded when you compile the kernel, and it will actually do the HVC instruction, which makes us to transfer from EL1 to EL2, and it puts the operation that we want on R12, the register R12. So if we'll go to Zen, actually this goes to an synchronous abort exception. The synchronous abort will get the registers of the CPU. It will check what is the cause, and sorry, I'll make a pointer. It will check the cause in this switch case, and it will see that we called HVC. I'm referring to ARM64 bit right now, but it has also cases for 32-bit as well. So let's say it sees that we got HVC. It checks some things for to see that the call was made from correct context, and then if so, it calls this call, which is do trap hypercalls. It gets the registers, and then it will try to make the operation that was requested from that HVC. So we'll go to this hypercall, and then it tries to check what is the operation that we want, and it will call, it will call the requested operation from this function table array here, and then it will get the request and come back to the guest. So let's see what is the operation. The operation is do console.io. It's the operation that was requested, and it's the appropriate position in this array. So then now we know that we want to do a console.io. We'll see what operation you want to do, read or write, and then it actually does it. So this is an implementation of paravirtualization. Is it okay? I guess so. So let's talk about virtualization of interrupts. Now, if we know how to virtualize an I/O, now we need to virtualize the interrupts for it, because we might want to, the controller wants to notify us to something. So in ARMv8, they added 2 more signals, which is called VIRQ and VFIQ. It's the same as IRQ and FIQ. FIQ is for more prioritized interrupts. And the hypervisor using the interrupt controller maps which interrupt goes to which OS, as well as some of them it needs to catch by himself because he wants to handle them. For example, it can be for example, a timer. So when we want to switch the OSs, because the hypervisor have some kind of scheduling process in order to give time both to both OSs. In our example, it's the same as in operating systems mostly. So now we want to be able to virtualize timers as well. So ARM made some corrections, or let's say additions to the generic timers they have, and they added virtual offsets. And there we use this virtual offset to determine the virtual count of how much time passed in the virtual world. Because then again, let's say we have a guest OS, 2 guest OSs that runs on this chip. Some 2 seconds in a real world doesn't mean that 2 seconds in the virtual world for, let's say, guest OS number 1 actually happened. So we are able to accommodate for that. So now we talked about everything that we can use in hardware-assisted virtualization in order to implement our hypervisor, main blocks, of course. But now we want to understand what do it require from our SOCs in order to use it. Basically, for hardware-assisted virtualization, which is what I talked about in my presentation, which is basically the hardware has mechanism to help us to do this kind of virtualization. You need any ARMv8 Cortex-A processor or ARMv7 Cortex-A with hypervisor extensions. This is a separate extension that the silicon vendor needs to pay for, okay? And of course, you need the BSP for the hypervisor needs a BSP for the hardware you are using. So, for example, you might want the hypervisor to have a BSP for your Raspberry Pi if you're using a Raspberry Pi for a virtualization solution. Keep in mind that everything I said you can implement on software and pure software only, except maybe actually everything you can do with software. So potentially every ARM core with an MMU does these things. Even without an MMU, you can simulate the MMU itself, but it will have a potential penalty for the performance you will have. And the costs for hypervisors are varying based whether it's commercial or not, which is something we want to address, because here I'm doing a discussion about why we should choose an open source hypervisor or a commercial one. Probably commercial one will cost more because of the licenses, the BSP, you need support, you need the royalties if it's for a serious production, for example. But most likely it will be certified in some way if you need it. For example, in automotive, aviation, or medical, you sometimes want it when you're talking about safety or security, and certification costs money. So open source, I'm not aware of open source hypervisors that are certified in that regard for safety. Maybe somebody here can enlighten us on that. But sometimes commercial hypervisor might be less tested regarding security because it's not open source, and then less people are seeing that the source code and doing evaluations. But still, commercial hypervisors can have certifications regarding security, for example, common criteria for EAL something. For example, Green Hills have an hypervisor that is certified for EAL 6+. They really like to talk about it, actually. Of course, virtualization comes with performance penalty because, wait, I think somebody wrote in the chat, so we'll see. Maybe have a question. Oh, okay. So virtualization will have a penalty performance in comparing to native, because then again, we need to have a context switch between the VMs, and we need to save all the general purpose registers and the stack pointers and the registers of the floating point unit. So that's need to be taken into consideration. Now, let's talk about when you shouldn't want to use an hypervisor, because that might be a consideration for your system. For example, when strong separation is needed, I actually would prefer to use two separate processors, because the main point of failure in this design is if I somehow hacked the type 1 hypervisor, I got control of the system and can do everything. Instead of, two separate CPUs, and then that depends on how I design my system. So that's a consideration. Second of all, if you're going to run a single Linux instance, you might want to use containers, because containers are they are not virtualization. There's just using C groups and namespaces in order to create a user space separation. It's less strict, let's say, because the container still exposes some of the things to the host of them, but it might be a solution for you if you are interested. And sometimes that's really depends on the use case. I took an example. Let's say you have a system that needs to run an application processor and have some kind of real-time tiny processing. So you might want to take a SOC that has an application processor with a tiny microcontroller, and it will be more cost effective for you. I looked for the internet online for just an example. Let's say for our example, we have Cortex A7 at 100 gigahertz and Cortex M4 that will cost us less than A53, and it might have similar performance depending on the system that you are designing. That's a consideration as well. And this, of course, doesn't take into consideration the royalties for the hypervisor if you're using a commercial one. That can be also increase the price. So that was my lecture. Hope you enjoyed it. And if you have any questions, that's the time.
Okay. So, anybody has questions? Thank you so much, Omer. And thank you all for attending. And And I hope you enjoyed this virtual meetup. Yeah, I mean, this time it's been a little bit different. I hope that like at least you were able like to enjoy this weird experience, and that you learned things that are relevant for you. Just like a little bit of announcements. So the winner for the raffle, I forgot to actually like ask for names over there. So number 27, I'll just say, I sent you an email, okay? Like, so you should check like your inbox. The title was something with number 27, and you'll get like either like a certificate exam or like an online self-paced course. So get back to me with email, and I'll give you like the details. We'll also do such a raffle, or even more, depend on how many people attend in the next session. And I want to, I'll stop the recording now, and I'll ask you like, let's like have a chat. We can also have the recording. I'll probably like cut it. And let's discuss like the next meeting, and let's see, first of all, what is your feedback about this one, whether you liked it or not, and when would you like to have the next meetup. So the winner of the raffle is Torbilot, and if you recognize yourself, reach out to me, and let's do it. Okay. And speaking of the training, then anybody who like wants more details on my stuff, please let me know. Okay. So, all right. So give me just 1 second. We're now a little bit less people, which is okay. I just want to hear from you when you would like to have the next meeting, and some feedback about it, especially since